Good afternoon everyone, I am Mr. Ish. Thank you for joining me for this video on verifying integral behavior. These will be a collection, perhaps 4 concept type questions regarding integrals. I have a book over here, the single variable calculus textbook, a college level book, where at the end of the chapter I've plucked out these questions from, and you have to show in these questions the verifying of these statements that will be placed before us. If this right here is one statement, we have to show or verify if this function is continuous on R. What does that R mean? It means that it's a function that has a domain minus infinity to infinity, a domain of all real numbers, and it's a continuous function. Therefore you could determine a derivative of this function at any point on that interval minus infinity to infinity. We have to show that this f of minus x dx is the same as f of x dx. Look at the intervals a to b and minus b to minus a over here. The constraints are these. The function is greater than or equal to 0, and we're looking at 0 in terms of the interval. A is larger than 0 and b is larger than a. If you just home in on these f of minus x and f of x, you're kind of thinking and looking at an even function, so that right there tells you quite a bit. How would you go about proving this, given the fact that we've looked at integrals so far? What we've learned, the best way to do this is using a substitution over here. If u is equal to minus x, remember we have to show, in these questions we have to show that these statements are true. If u is equal to minus x, then du is equal to minus dx, and dx is equal to minus du. If you're doing a substitution over here and you have a definite interval involved, you have to change the intervals. u1 is equal to, everything is being looked at in this form, minus a, and u2 is equal to minus b. We also have to keep in mind this, du is equal to minus dx, because that will play into this showing or this verifying. Let's bring the items that we've brought into this picture into our new integral. We have u1 minus a, u2 minus b. We have a minus sitting outside because dx is equal to minus du, f of u du. If you look right here at du is equal to minus dx, and you can reapply this to here, what you can do is bring a minus right outside. You have everything else over here. This minus applying outside allows you to flip the intervals back, such that you can bring minus a on the top and minus b on the bottom. You have f of x and dx come in. When you open this up, these minuses cancel out. You have a minus a minus b, f of x dx, and you end up showing that this left hand part is indeed equal to the right hand part, simply because this question is quite interesting in the fact that we're looking at an even function. Let's look at a realistic example over here. If supposedly f of x over here was representing a cosine x, which you know is an even function symmetric about the y-axis, if you were to look at it just generally right over here, minus pi over 2 and positive pi over 2, here you have 0 comma 1 right here on the top, and we know we have to deal with an interval a and b. A can be right over here and b can be right over here. We can determine these two values a and b. Let's say a is equal to pi over 4, because we know a is larger than 0 but it's less than b, and b is equal to pi over 3. If we plug in these items and the function into this schematic, see exactly how things will play out. You'll have pi over 3, pi over 4, cosine of minus x dx. Here you'll have a flipped interval. You'll have a minus pi over 4 and a minus pi over 3 cosine x dx. Let's see how everything plays out over here. Cosine minus x, we know it's an even function. It becomes and it stays cosine x. Cosine x is equal to cosine minus x. It's a trigonometric identity. What's the antiderivative of cosine x? It's sine x. And then we're looking at everything here from pi over 3 to pi over 4. The antiderivative of this cosine x is a sine x, and we're looking at everything here from minus pi over 4 and minus pi over 3. If done correctly, these two answers should be the same, which will end up showing that this is equal to that. Let's look right over here. Sine, you know you have to put the upper and the lower and you do the difference of the two. Sine pi over 3 is a sine 60, which is a root 3 over 2. Sine of 45 is a 1 over root 2. We can just keep the answer as this. Let's look right over here. We're looking here at minus 45 and minus 60, but you have to adjust everything here with regards to 0 degrees. So you're looking down over here. So what we end up really looking at here is a sine of 315 minus sine of 300, right? Because 360 minus 60 is a 300, 360 minus 45 is a 315. Let's plug in these values. You know in the fourth quadrant, sine is always negative. You'll have a minus 1 over root 2. because the reference angle for 315 in the fourth quadrant is still a 45, but it's a minus 45, and you'll have a minus 1 over root 2 come out. You have the minus coming from right here in the equation. Remember the upper and the lower limit and the difference, that's the difference. Sine of 300 is equivalent to sine of minus 60 in the fourth quadrant. You'll have a minus root 3 over 2. These are just trigonometric ratios at play. Open this up or simplify, you'll have a minus 1 over root 2 plus root 3 over 2. Minus 1 over root 2 plus root 3 over 2. Both of these end up being equivalent, and they are indeed equivalent. So you end up showing that this continuous function, in this case being a cosine x, an even function, f of minus x interval a to b is the same thing as saying f of x dx from minus b to minus a. Nothing too hard, but we've shown you this. Now this next question is another one you have to show, and we'll just try to breeze through this one. If this function is continuous on an interval r, all real numbers minus infinity to infinity, we have to show this f of x plus c dx from a to b, lower to upper limit, is the same thing as f of x dx, a plus c to b plus c. It's not hard. Think about polynomial substitution technique and roll with that, and you will be right, and you'll end up verifying this is equal to that. If u is equal to x plus c, du over here is equal to dx. Du is equal to dx because the derivative of x plus c is simple polynomial expression, is just going to be a dx, because this comes out as a 1, this comes out as a 0. You have to develop new set of intervals because of this substitution. Everything will go right over here. u1 is equal to x plus c, a plus c. u2 is equal to x plus c, but b coming right over here, which will be a b plus c. Then you have to reword your original interval and integral with these new substituents. u1 is a plus c, u2 is b plus c. You have a f of u du, but how can we show that this is actually equal to that? You can do so by focusing on this part. If du is equal to dx, dx is equal to du, function with regards to u must be equal to function with regards to x. A plus c, b plus c, f of x dx, and we end up showing that it's the same. Again, du is equal to dx, so all of this right here melds right into there. It's not a hard question. The trick to this type of question was to understand that you had to bring the polynomial substitution technique into play over here. Once you realize you can do that, your intervals come into play very easily. Let's look at this question number 3. If a function is continuous, we have to show that this side is equal to this side. Function with regards to cosine x from interval 0 to pi over 2 is equal to a function with regards to sine x from 0 to pi over 2. It's not a hard question because all we have to do is show that that is equal to that. And you don't need to be thinking about polynomial substitution technique over here. You can just think about direct solving of this question. That is, you do your definite integration procedure. The antiderivative of cosine x is sine x. From an upper pi over 2 to a lower 0, antiderivative of sine x is a minus cosine x. From an upper pi over 2 to a lower 0, you could technically bring the minus outside and there'll be nothing wrong with you doing that. If you look at this in terms of its answer, you have sine 90 minus sine 0, you get a 1. 1 minus 0 is a 1. Here you have a minus cosine 90 minus cosine of 0. You have a minus 0 minus 1, which is equal to 1, and they both check out. This is equal to that. Numerically, in terms of their definite integration, the answers are the same. The reason why this works is because of the effect of this minus, and because of the opposite in nature of their derivatives. You remember, if you think about sine x, the derivative of that is a cosine x. When you think about the derivative of a cosine x, you get a minus sine x. But when you know you're looking at in terms of integration, when you look at the integral of sine x, you get a minus cosine x. But when you look at the integral of the cosine x, you get a positive sine x. Because of the opposite effect in terms of the derivatives and the integrations, and the positive and the minuses play out, you end up having exactly the same answer. It just plays out that way. This right here is the last question for this video, a conceptual question. If a function is continuous, we have to show that this cosine square x dx from the interval 0 to 90 is equal to sine square x dx from 0 to 90. You have to think about here the power reducing formula, or as some people call it, the half angle formula. 0 pi over 2, you have 1 plus cosine 2x over 2 dx is equal to 0 to pi over 2, 1 minus cosine 2x over 2 dx. Now we've not literally talked about the power reducing formula in terms of integrals, but you've seen it in the derivation videos like the sphere derivation, the circle. In those instances you've seen this come into play. If you split everything around each of these positives and minuses and you expand the intervals, this is what you'll get. You'll have 1 over 2 pi over 2 0 dx plus 1 over 2 cosine 2x dx from pi over 2 to 0. See, I split everything around this positive sign, this expression. I'll do the exact same thing over here. I'll have 1 over 2 0 to pi over 2 dx minus, I'm splitting everything around that minus. I have this 1 over 2 0 pi over 2 cosine 2x dx. If you focus here on this 1 over 2 dx and this 1 over 2 dx are exactly the same. If you take them on each side of the equation or on one side, they'll cancel out, so we don't even have to look at that. What you end up remaining with is just 1 over 2 cosine 2x dx from pi over 2 to 0 is equal to minus 1 over 2 0 to pi over 2 cosine 2x dx. Now you would think, how can these equal to one another? They can, and we'll show you. If you want to be even more clever, you can eliminate the 1 over 2, because technically you can take this 1 over 2 on the other side, it'll cancel out. This 1 over 2 will become a 2 divided by 2, and it'll cancel out. So now what we're left with is just this. You can do a polynomial substitution. If u is equal to 2x, du is equal to 2 dx, and dx is equal to du over 2. Why are we doing this? Because we have a composite here. Then the intervals will change. u1 is equal to everything with regards to this. 2 times 0 is a 0. u2 is equal to 2 times pi over 2 is a pi. And everything will beautifully play out, and you'll see it. You'll end up having a 0 to pi. You'll have a cosine u du, but you have this 1 over 2 because dx was now equal to du over 2. On this same side, use the same letters, same substituents. You'll have a minus 1 over 2 0 to pi cosine u du. Now how this works out is when you look at the antiderivative of cosine u is a sine u. You have this 2 sitting outside, you can bring as a denominator, you have a pi and a 0. Antiderivative of cosine u here is a sine u. Again, you have a 2 sitting here, but you have a minus here on the outside. Again, from a pi to 0. The reason why this will work out is when you do the definite integration procedure here, putting the pi over here and then the 0 here, and likewise here, pi and a 0. Sine of pi, or 180, minus sine of 0 is just a 0. You end up getting a 0 coming out from this part right here. 0 over 2 is just a 0. Here you do sine of 180 minus sine of 0, you still get a 0. Here you get like a minus 0 over 2, which is still a 0. So 0 is equal to 0, and we end up showing that this is equal to that. And you show it by means of this power reducing procedure, or the half angle formula. Simplify the initial expression right here, this expanded integral which develops, simplify it, take it down, and at the definite integration procedure is where you end up showing that 0 is equal to 0, so this is equal to that, and you've satisfied what the question was asking. That'll be it for this video. I hope you enjoyed these questions. Remember, at any point you're looking at your textbook, you can always go to the end of the chapter questions. It is there where you end up finding some of these questions which are more theoretical or conceptual in nature versus the ones which are more numerical in nature. Thank you for watching. Have a nice day.